Good evening and welcome everybody. This is Obi-Wan Pez for Simplex Pachinko. How are y'all doing? We are going to be looking at some new Mathematic Educator puzzles. Just as a word of warning, I have not seen these yet. Alrighty. So... SQJA. Proposed by the solutions editor. The four midpoints of a trapezoid's four sides are connected with four line segments connecting adjacent sides, forming a quadrilateral. What must we be able to conclude about this quadrilateral? So I am going to draw a very I don't even know, like a stereotypical sort of trapezoid here that is not particularly any sort of shape, has any particular properties or anything like that. So we're going to look at the four midpoints. So roughly speaking, here and here and here-ish and here-ish, connected with these four lines. Alright, so what must we be able to prove about these particular pieces? So, let's see. These are going to be the same here. These are going to be the same here. The two opposite sides, the ones that are parallel, do not have to have any particular relationship to each other. The angles do not have to have any particular relationship with each other, except because these lines at the top and bottom are parallel, we do know that our opposite interior angles of that's going to be rough. Because we don't want to put two hashes, because that probably belongs on the other one. Right, so over here, this one here is going to have two hashes, as is this one here. This one will have two hashes and a cross, not pi, as will this one here. Okay, so what does that tell us? We have triangles that have 3 and 2 and 2 and 4. Okay, so nothing yet. Because it is a trapezoid and not necessarily, anyway, a parallelogram. Okay. Trapezoid's not a superset of parallelograms. Okay. Now, this might be a little crazy here, but you know what? Let's expand this a bit. Because this is going to become a really small... That's much better. Alright, now you can see my handiwork doesn't even connect. It's all good. Alright, so... if we were to extend this further... right, so if this line were to keep going this way, it would cross our blue line here, and it would have angles here and here. Wow, that's not even the right one. Awesome. Okay, so here and here would have to be the same. Oh, look out. We've got some congruent triangles. Blaine, then. How's it going? DJ shortest path. Not really. But as always, let's try to look it up. Dijkstra's algorithm to find the shortest path between A and B picks unvisited vertex with the lowest distance, calculates the distance through it to each unvisited neighbor, and updates the neighbor's distance if smaller. Okay. So, actually, yes, I have seen this before. Using, or in a classical combinatorics. So, I won't necessarily get it right because it has been 15-ish, pretty close to 15 years now. So if we were to take a little bit of a break here. All right, let's do this. A, B, C, D, and E, and then make up some numbers. So like 1, 4, 6, 3, and 2. So if we want Distance from, here we go, A, B, C, D, E. And this might be messing with the way you're used to these being set up, but whatever, it's fine. Okay, so we can make a table out of it. Good evening and welcome anybody who just came in. My name is Obi-Wan Pez. This is NSimplex Pachinko, your home for all things mathy. Welcome to the stream on this Tuesday night. So if we want to go from A to A, B to B, etc., these are all just 0, so they don't count. Since this is an undirected graph, then we don't have to worry about, you know, traveling from one thing to another. We just need to calculate half of them. So this is going to be a I forget what kind of matrix they call it. Anyway. So for mathematicians, we'd start with something like this. And we'd say, okay, to go from B to A, which is going to be the same again as from A to B, we would look at the distance between them, and we find that that's just 1. So this only requires 1 movement. That's it. Hang on. 1. All right, to go from C to A, it is again 1 move, and its direct distance is 6. To get from C to B, or likewise from B to C, we have to make 2 moves. So here we have to go from C to A, and then to B. So this is going to be a 6 plus a 1 is going to get a 7. To get from D to A, that's direct, so it's 3. D to B is a single move, is 4. D to C has to be 2 moves. So we have options here, but there's only one that actually makes any sense. It's going to be from going from D to A to C. There is the possibility that if the BD connection were better, so if, for instance, this were only 1, then we can make 2 moves going from D to B to A to C, using less, you know, energy, fewer resources, whatever it is, compared to the 3 to go from D to A and then A to C using 6. Well, so here's the thing, you would only look at like 1 movement at a time, and I think that's probably where the Dijkstra algorithm is coming in, is that like it's only really looking at like 1 step at a time, looking for the shortest path. So in this case, D to C is again DAC, which is going to be 3 plus 6 is 9. E to A is going to be EDA, which is going to be 2 plus 3 is 5. E to B. So here's the one that, sorry, change that back. Oh. I managed to make it so that it doesn't actually matter which route you take. E to D to A to B has the same amount of resources that are going to be used as E to D to B direct. So because DAB and also DB are 4, a sum total of 4, it doesn't actually matter which path you take. Now it is true that D to B direct is going to be shorter. So I don't know if that matters. But either way, E to D is 2, and then D to B through either of the avenues you could take is going to be another 4, so that's going to be 6. Right, E to get to C. In this particular case, going E, D, A, C is going to be 2 plus 3 is 5 plus 6 is 11. And then E to D is just 2, it's direct. So you can make a list that, yeah, like you can definitely get an algorithm. There's something else that goes on though, is it said it wants to like update its neighbor. So I have to, unvisited, okay. Okay. Okay, interesting. Yeah. So let's again change this slightly. You know what, let's use the one that's in the example on Wikipedia. It's always dangerous to do this sort of stuff, but whatever, it's fine. It's on Wikipedia, so it's public, right? All right. So A to B. All right, so I'm going to put other labels on these just for ease of mentioning where we are and things like that. But realistically, right, it doesn't particularly matter. Okay. Okay, pick unvisited vertex with the lowest distance. So it's going to look at all of the, again, we want to go from A to B. Right, we want to find the lowest distance that it's going to take to get through this. Now, keeping in mind, this is a computer algorithm, so whereas we can just probably look at this and say like, okay, I know what the easiest path is going to be. I know what the shortest path is going to be. You won't always figure that out like super easily with a computer. Okay, so it said mark each of the nodes with the distance starting from A. So man, okay. So it says that we're going to follow this path. We're going to go from A to C first, and we know that this is going to be a value of 7. We know that going from A with a value of 0 is going to cost us 9 to get to what I've labeled D here, and it's going to cost us 14 to get to what's labeled E. So then, no, we're good. So then we go to, now we're out of moves. So we say, okay, we're not going to use this one anymore. We go over to C here, and we say from C, what's this going to get us? So we have, in order to get to F, we either have to take A to C to F, which is going to cost us, if we go this way, that's going to be 7 plus 16 is going to be 23, which seems like a horrible idea. Or it's going to cost us 7 plus 10 to get to D is going to be 17 along this path. And since 17 is greater than 9, we would never select this path. Okay. Other way to get to D is going to be from taking A to D direct, which is 9. We already have that. Right, so 17 is greater than 9, so we just cross it out. 9 is already here. If we wanted to go to F, that's going to be plus 11, which is going to get us 20. And again, here, 20 is less than 23, so that would be the good way to go. This would be the horrible way to go. Don't go that way. Now that both of the paths from C have been debunked, essentially, like we can't go ACD because we could just go AD for cheaper. And we won't go ACF because we could just go ADF for cheaper. So C is out. We have no more connections. So like I said, I have seen this before. It's just been a really long time. Which is the crazy. I mean... So whenever you're talking about a graph, yeah, computer science and mathematics have always kind of gone together, but then like nobody wants to admit that they're almost the same thing. Okay, so then we don't have any more paths to get to D, so we know that 9 is going to be the winner for that one. It's going to take us 20 to get to F. It's going to take us 9 to get to D. And then, oh, I guess technically we could have also tried getting to D via E, which again is going to be 14, and then plus 2 would be 16. We already know that that's greater than 9, so there's no point in ever going there. Then we would try, okay, from E, we could also then go to B, which is, again, the goal, but your algorithm will not be able to discern that, right, immediately. It's not going to say, well, or it's going to say to itself, well, it could potentially be faster to go from A to E to D and then somewhere eventually get to B. So it doesn't know any better. It's just a computer algorithm. Right? And if you're writing this in general for any sort of graph, then you won't necessarily like discount the possibility that there's like some weird winding path that will eventually get you to B. Drop rate is the highest because everybody assumes that computer science is programming. It's not really. Like, some of it is programming, but a lot of it is trying to figure out the architecture of computers itself. What is the science of creating a computer, of creating programs, of, you know, like all of it? How do computers actually work? You need to know that. You don't necessarily need to know that in order to program. Somebody who has no degree at all could do awesome programming. You know this. But if you want a degree because you want to get into a prestigious program or whatever else, then you need to understand how it all works. Oh, right, I forgot one other path. A to D to E. A to D to E is going to be 9 plus 2, which is 11. Which is, 11 is less than 14, so 14 is out. Which means that this is the best path in terms of the shortest distance from A to D. And then either, we don't know yet, wink wink nudge nudge, we don't know yet whether it's going to be better to go from A to D to E to B, or A to D to F to B. Now, we know, again, it's obvious that going from A to D to E to B is going to be the best way to go. But computers don't know, so you got to kind of spoon feed it a little bit. And again, it's checking all of this stuff in real time, so it's very fast. Okay, so then we've got 11 to get to E, and then we've got 9 to get to B. So this is going to be 11 plus 9 is going to be 20. On the other side, we've got 20 already, and then 6 from F to B, so 26. And since we know that 26 is greater than 20, 26 is not going to be the path we choose. Therefore, we're not going to choose the path containing F. We'll only choose the path containing E. So A, D, E, B. And keep in mind, you don't know which one it's going to be until you actually do it. Nah. I could teach cross-listed classes, probably no problem, but I don't know enough of like the algorithmic side of all of these different programming languages and things like that. So, yeah. So A, D, E, B. Give me 1 second. a capital B. I remember a couple of other things that Dijkstra did, which were very important to, you know, mathematics in particular, and like I can't remember any of it now. It's been such a long time. Yeah, and log n algorithm. I mean, log n if you can help it, but most of the time you can't. Yeah, so the problem with this one is that, you know, it's what's the O complexity on this one? Big O complexity is, I mean, it depends on the number of nodes per, or number, excuse me, number of connections per node, but in theory, right? I guess it's got to be n squared, because you have to come up with all of this stuff potentially. Maybe a little bit bigger. Never. No, I don't know algorithms, not really, well enough to teach any of that stuff. But you know, if you want to look at a particular algorithm like this, which is actually mathematically based, which is actually from, like I said, combinatorics, then, you know, this is something I can do. We could talk about Hamiltonian paths. We could talk about all sorts of cool stuff. It's just going to take me a while to remember it, that's all. Oh, that would be interesting. If this is a, I don't know what you would call it exactly. Not a kite precisely, but if this was a quadrilateral which had opposite angles equal to each other, is it a rhombus? That would be very convenient. Okay. So if we extend this out, if we extend all four of them out, and again, if we extend all four of these sides, or the diagonals out, which, I mean, they're not diagonals, they're the connections between the midpoint, adjacent midpoints. So here, this would get us 2 here, it matches with 2 here. Ooh. We're getting close. Yes. Okay, so they are not necessarily exactly the same size. In fact, they can't. It depends on the angles. 3 here, 3 here. 4 there. 4 there. I should probably just label them with numbers or something. Can. I think it would be rather arduous. I'm not saying you couldn't do it. It just, you know. Ugh. Okay, so we could do like a degenerate case where we start with a rectangle and then work its way out, or parallelogram, and then work its way out, but I think that's going to be too easy. Don't mind me just crunching rocks over here. Jeez. Adjacency matrix? I mean, I don't know if that's the right name for it. So like A, B, C, D, and those angles will be the interior ones that we're talking about. The angles do not have to necessarily be the same. Adjacency? Adjacency? Can't say I know that one. Directional graph, yeah, okay. Mm-hmm. I've heard the name of it, but okay. So we've got this like alpha, beta, gamma, and delta, which are the angle measurements for each of these. Supplementary to each other, so we get alpha out here, we get beta out here, we got delta out here, and gamma out here. Okay, so now what? So weirdness. If this is alpha here, and this is beta here, they're supplementary to each other, then this angle here, marked with 2 hashes, and this angle here are going to sum up to beta. I don't like this, but could make it happen. Ew. Boolean flag to define the adjacency matrix in direct graph. I'm going to be a pain in the ass here and say those are words. I unfortunately do not know. Bertram! How you doing? Okay. It's like we could split these up into beta 1, beta 2, which would be like subdivisions of beta. This is going to be really ugly. This is just to have something to do, by the way. This is not necessarily the best way to do this. Bertram, I believe, is a bit farther along, but I don't remember. Sorry. I'll also let you speak for yourself, that's fine. Okay, so by the same token, we get like this is alpha 1 and this is alpha 2. This is alpha 2. This is alpha 1. Like I said, this is probably going to be a horrible idea, and don't ever do this at home, but you know. But alpha and beta do not necessarily relate to gamma and delta. Because this is a trapezoid and not a parallelogram or anything like that, it can be just about anything. So to anybody who missed it, hi, my name is Obi-Wan Pez, this is N-Simplex Pachinko. We're working on a problem that came from Mathematic Educator. This is the Student Quick challenge. So, yay. Right, yeah. Right, so non-directed, you need m by n over 2, and directed, you need the full m by n. Yep. Alright, if this is gamma, then this is going to be delta 1, delta 2, and if this is delta, this is going to be gamma 1, gamma 2. So this thing here is gonna be 180 minus alpha 2 minus beta 2. This is gonna be horrible. This is gonna be 180 minus gamma 2 minus delta 2. Yeah, let's not do that. Oh, by the way, I think I cracked something that I was working on earlier. Or at least sudo cracked it. I need to know if anybody wants to take up the challenge on this one. I need to know if there... Does there exist a set of 3 perfect square numbers that are linearly separated, or can form an arithmetic sequence. So the thing that I'm looking for is a squared, b squared, c squared, where we could rewrite this instead as b squared minus x, b squared plus x. Now, it is probably easily enough done by an algorithm, and I just am particularly lazy at the moment and not feeling like doing this myself, but realistically, I just haven't opened PyCharm in a year at this point. Do I even have it on this computer? Oof. Alright, and then the extension on that. Find, well, really b squared, but find b squared such that there are 4 or more such x values. So 4 or more sets of 3 squares, all of which are centered around b squared. There's a reason for this. I have no idea if it's even possible or what the like how easy this would be to prove slash disprove its existence or non-existence. All I know is that right at this exact moment in time, I'm not feeling it. I'll get around to it eventually, but if anybody else has a quicker answer and can figure this out soon, yeah, I don't know. Make it co-author or something? I don't know. If anything actually comes of it, yes, I will happily co-author a paper. Let's see, this is a gamma 1. This is going to be 180 degrees minus alpha 1 minus delta 1. And this is a 180 degrees minus beta 1 minus gamma 1. Okay, so there's a certain other thing we can do here. Let's see. So this is supposed to be a quick one. Sheesh. So if we make this much more exaggerated, right? We've still got the things. Still got our midpoints. Might be a rhombus still. Unlikely, but it's possible. No, it's not a rhombus. Definitely not. Never mind. Could maybe be a parallelogram. Okay, so the question here really is, if it is a parallelogram, that would do it. Yeah. If it is a parallelogram, then the opposite angles on both of our corners should be the same. idea, but if we were to let 180 degrees be alpha plus beta, weird ideas are usually what, you know, how things go. Okay, so if this is true, then we've got alpha plus beta minus alpha 1 minus delta 1. Alpha minus alpha 1 is going to be alpha 2 plus beta minus delta 1. Right, this angle here is all of that stuff. It's going to be alpha 2 plus beta minus this other stuff. It's not equal to anything that we know of. At least nothing we've proven, right? No, that's not it. This one's delta 2. Okay, so then also we've got all these triangles that we've got scattered all over the place. We know that this length here is going to be the same as this length here. This length, that length are the same, but that doesn't necessarily help anything. Alright, since this is taking me forever, I did take a hint here. So draw a diagonal. this is parallel to that, which is the same as all the rest of the line down there. Then we've got an angle here and an angle here, which are the same. Oh, and the large triangle that we just drew here is going to be similar to, because we also have this angle here similar to, or that angle is going to then be congruent to this one here. We don't know that yet. Nope, nope, nope. Okay, this one here is going to be congruent to this one here, right? The other half of that angle, because again, those are parallel to each other. Again, we know that this and that have to be the same size, and that this and that have to be the same size. These are in a 2-to-1 ratio with each other compared to this one. That by itself doesn't prove anything yet. However, alright, side lengths are in a 2-to-1 ratio. So that's two sides. They share an angle. C. Okay. I need one of the other angles to be proven to be the same. Or I need to prove that the third side is in ratio. Right, because it could... I don't think I do. So we don't necessarily know anything about the angles, but we do know one of the angles, which is shared. And then the ratios of two of the sets of sides are 2-to-1. Is that enough to show anything? I mean, in my mind, I'm convinced, but but then again, I know, you know, ahead of time that this should work out the way I want it to. Side angle, side similarity. Side angle, side similarity. If, let's see, angle C is congruent to angle C, so check. And then AB over XY in this particular case would be B here, A here, D here. And MBC and MCD. Why not? So in this particular case, BC compared to MBCC is going to be the same as CD over MCDC. The angle inscribed by the two sides in both triangle are equal. It's not really helping me in terms of like showing the proof of how that works, apart from just right here. So let's see. So how to go back the other way is really going to be a Okay. Yep. Okay. All right. All right. All right. So here's how to prove it. So assume that you have your two triangles. So A, B, C. D, E, F. So what you do is you take length AB and place it here, such that that is parallel to that. So basically you're just copying the original triangle and slapping it onto this other one. Right, DQ equals AC. Oops, Q. Yeah, B prime, C prime, A prime. Okay. Right, so here, got that, and then we know that this angle is going to be the same for both of those. Alright, so then we don't know that they're parallel yet. AB over DE. Alright, we have the similarity of their sides, or at least the ratios. So dB prime over dE is going to be equal to dC prime over dF is given. Therefore, y'all are using acronyms that I don't know what they are. BPT, so parallel theorem probably. That doesn't necessarily help me at the moment because I don't know what BPT stands for. Basic proportionality theorem. Okay. If a line is drawn parallel to one side of a triangle intersecting 2 points distinct from each other, then the other two sides are divided in the same ratio. So the converse of that is that if the other two sides are divided in the same ratio, then the line that's drawn from one side of the, from one side to the other is parallel to the bottom line. Okay, so I already wrote that way long ago, but nonetheless, this is going to be parallel to that by proportionality. Okay, so that now, since that's the case, all right, since they're, since they're parallel, now we can say that they have those, and therefore they're similar triangles. Okay, so side angle side similarity, as long as your side lengths are in ratio to each other and the angle between them is the same, then we're good. So here we could say that, yeah, we've got BDC, BCD. All right, triangle BCD is going to be similar to triangle MBC, MCD. And by the same theorem we were just using, this is going to be parallel to that. And then we could do the same for MAB, MAD with A to make that triangle. And then that's going to tell us that this is parallel. And then we're going to get right, without loss of generality, we could do this. We could do it. I don't think we probably need to go through it, but at any rate, those are going to be parallel. And so that's going to mean that our, the shape inside is going to be a parallelogram. Now, in theory, I could have made that come out of this mess, but I don't know how long that would have taken me. Especially if I'm relying on algebra rather than geometry. Oh. Maybe not. I had drawn one of these diagonals, okay, whatever, would that have then done anything here? Interestingly, because this is 180 degrees minus beta 1 minus gamma 1, right? The sum of these two angles here ends up being beta 1 plus gamma 1. Doesn't necessarily tell us anything about it, but at the same time that would say that yeah, okay. We wouldn't be able to use this, but right, because it's using what would be needed to be proved, but each of those is beta 1 and gamma 1 respectively, because this would also be parallel here. Now again, we don't know that ahead of time, but is there something else we could use? At this point, it's almost just purely academic, because nobody cares, I'm sure. Anyway, SQJA SQJV. Suppose rectangle INSC with dimensions x times y is inscribed inside of a rectangle REKT, get wrecked, with dimension c times d. Prove the perimeter of rectangle INSC cannot exceed that of rectangle REKT. Oops. Oh, inscribed. Inscribed. So when is xy going to be less than CD, or can we guarantee it? Perimeter, not area. But it's basically the same thing. Twice x plus y needs to be less than twice c plus d. Right, the perimeter of inscribed cannot be or equal to. So that is x plus y. It needs to be less than or equal to c plus d, and then prove it somehow using algebra or what have you. Make sure. Okay. This whole thing here is D. This little piece in here is X. This piece here is Y. Nope, other way. Close. Okay. I think that this whole shape is just not going to work, but we can pretend to make it work, and then it's gonna hopefully just fix some stuff. That's fine. We do all this like pretending all the time. All right. Yes, this is 100% totally a rectangle. I don't know what anybody else would be talking about here. And I did check it. It does say rectangle, so. So I-N-S-C for inscribed. Very imaginative. So here we have dimension X and dimension Y of our rectangle, which is definitely what it is on the other sides as well. Right, and then what we do is we can say, okay, we've got pieces of this rectangle, let's go MN PQ, cuz. Okay. Yep. Alright, here we go. So, in all the cases here, we have m plus n needs to be greater than x, and also p plus q needs to be greater than y. And also, if it's a rectangle, then this is also definitely going to be m, and then this is going to be n, and this is p, and this is q. Right, if it's a rectangle. We could probably also prove this even without it, but it doesn't matter. So twice m plus q plus n plus p is going to be greater than or equal to 2x plus y. And then this is going to be 2c plus d. Woo! Alright, if anybody else has any questions, please let me know. My name is Obi-Wan Pez. This is nSimplex Pachinko. Alright, now to a real problem. So J1 states that the sign of n cannot vanish at any non-zero integer n. So sign of n by itself is not going to be 0 when n is an integer barring 0 itself. Okay. Prove there exist infinitely many integers n such that the absolute value of the sine of n is less than some epsilon arbitrarily small epsilon, which is not 0 itself. So out there we can find an infinitely large set of integers n, such that when we take the sine, it is within whatever distance we want to call epsilon. So this is saying that if we take sine of n plus delta, we will get 0. This is what I'm getting for arbitrarily small delta, which is itself not 0. Okay, so this is what I'm seeing. This means that with our trigonometric knowledge, we can break down the sine of n plus delta into the sine of n times the cosine of delta plus the cosine of n times the sine of delta. Right? Like signs, unlike functions for the sine function. Okay, so this says that if we had the absolute value of n minus hang on x minus oh man. So we're essentially using the limit definition here. Epsilon delta proof. Woo. It's not quite the same. Okay, so here the goal is that we're taking sine of n minus 0, our target. So this is distance between sine of n and 0 is arbitrarily small, so it's less than epsilon. realistically, right, this is saying that the distance between n and some k times pi, because that's going to be our zeros for the sine function, it's going to be less than delta. Alright, so here, distance between n and some integer multiple of pi. Okay, so k has to be an integer. Is arbitrarily small. And realistically, we have to show that this is true. Show the implication that if we start with the distance between our two x values, our two input values, then we end up with that relationship. Alright. If we do this, this is approximately 1, this is approximately 0. This whole thing right here is approximately 0. If we do this bit, this is the relationship we want to work with. So we can back that off just a little bit. So this cosine of delta is going to be pretty close to 1, but nonetheless slightly less than. Just the sine of n by itself. Absolute value and all that. Alright, sine of n plus delta. It's going to get you this. Oh, okay. So this can go here, essentially. Which means that the value of n plus it's gonna be a little weird. You know what, let's go like that. That preserves it, right? Squaring both sides of an inequality. As long as they were both positive to begin with, which they are, because again, absolute value on the left, then this is going to preserve this inequality. That's going to get me a little stuck because I need to undo the... I need to undo the sine function. If we assume that delta is only positive, is that legal? Oh. Okay, maybe I should have done D first. SQJD. Says prove if n is any integer not 0 itself, then sine of n is not 0. So realistically I should have done that first, but you know, whatever. Okay, so if so sine of x, we'll just do x, equals 0 is going to imply not therefore. X is going to be equal to some k times pi where k is an integer. So sine of n equals 0 is going to imply that n equals k pi, and therefore pi equals n over k, which makes it a rational number. Alright, so we know that this is a contradiction. So therefore, sine of n cannot be 0. Unless n equals 0 itself. Alrighty. Okay, so maybe we can use that here. Meh. Absolute value of the sine of n minus 0 less than epsilon. I might be splitting hairs here, or trying to like use the definition in the proof for it. So the sine function being an odd function should mean that we can, in fact, use the absolute value on the inside instead of on the outside. So if we want to get really technical about it, we just look at the definition of what is absolute value. It's the absolute value between two particular values, you know, x minus a. It's going to be equal to just x minus a when x is greater than or equal to a, and negative parentheses x minus a when x is less than a. So here we know that the sine function of n plus delta minus 0 exists when it's gonna be ugly. Greater than or equal to 0. And negative parentheses. Sine of n plus delta minus 0 when sine of n plus delta less than 0. Yeah. Well, okay, so that doesn't quite work. But if we restrict it to arbitrarily close to n, this should work. Okay. This is the absolute value of the sine. So then here, this is also going to be oh, interesting. This could, in theory, be n plus delta greater than or equal to. This is the inverse sine of 0. Which can make that k pi. And this could do the same thing. Again, this is going to be small values of delta. I like that any better. Okay, so I'm not convinced this is the best way to go, but it is certainly a bit interesting. Alright, so I think, really, right, we've just bumped this in. So now absolute value n plus delta is going to be less than the inverse sine of epsilon. And so that's going to be our relationship. Or if we say that this is just going to be n minus a the whole time. Right? N minus k pi. Oh, yes. That would do it. Duh. right, it equals 1 here, it is equal to 0 there. So this is literally equal to 0. Limes! Sort of. I mean, yes, but at the same time. So we're trying to prove that there are an infinitely many number of integers n, such that the absolute value of the sine of n is less than some arbitrarily small number epsilon. And of course, I was given the hint here, or it became obvious to me that the best thing to do would essentially do a delta epsilon limit, and show that this is the this is the way to go anyway. So I need to actually erase a bunch of the stuff that's in here. It's fine. It's fine. Okay, so what we were doing was n minus k pi and this was for our n minus k pi alright, the distance between these particular numbers. Okay, so if we were doing this as n minus k pi is going to be greater than or equal to some, hell, j pi. Alright, so we were essentially saying, like, we can take the inverse sine of both sides here. The inverse sine of 0 is going to end up being just some j pi, some integer. And again, as long as this is small values of right, small values of n minus k pi, as long as these are very small numbers, then we're going to end up with n being, in the top case, greater than or equal to k plus j, parentheses pi, which is just an integer. And then n is less than k plus j pi. So we've got our sine value, which, whether the absolute value is on the inside or outside, it doesn't matter. The sine of an absolute value is an even function, so it's gonna curve out both ways like that. We wanted it to be very close to oh, sorry, that's not a delta there, or a plus, n minus k pi, like that. Right, as long as these are small values, this relationship's going to work out. And whether or not the interior portion of the sine or the exterior portion of the sine is what's being absolute valued, it doesn't matter. And then that's just going to be, you know, take the inverse sine of both sides of this. Right, it was less than epsilon. So that gets us this, which again, absolute value n minus, okay, pi should be less than delta. Therefore, choose delta equal to the sine inverse of epsilon. For the edge case. So we're saying for this particular thing, then we can say right. Assume there are an infinite number of hang on. All right, let's go back. Okay, so assume that there are an infinite number of values No, it works. It's just I need to remind myself exactly what it is that I'm allowed to start with. N which are arbitrarily close. No. Arbitrarily close to k times pi, with k being some integer. Positive, negative doesn't matter, although it can't be 0 itself. So the distance between n and that k pi is going to be less than delta. Right? Some random delta. Totally random. Alright, we choose delta equals inverse sine of epsilon. It's the absolute value n minus It's going to be less than the inverse sine of epsilon. If we take the sine of both sides, we get the sine of, nope, absolute value, n minus k pi being less than epsilon. And all right, so absolute value of sine of n minus k pi is equal to sine absolute value n minus k pi. All right, so reason being, sine is an odd function. And this is again for small values of n minus k pi. We need not make any sort of grand gestures. We don't have to prove all that stuff that I did up there. We don't have to do the definition of the absolute value and all that. We need not work out the particular. Of, you know, any particular sine function, whatever. Okay, so now we have the absolute value of the sine of n minus k pi. Nope, not there. Is less than epsilon. And then we can break this down into the absolute value of, we break this down using the sine sum and difference rules. So this is going to be the sine of n times the cosine of k pi minus cosine of n sine of k pi less than epsilon. So the cosine of k pi is going to be equal to 1 or negative 1. But this being an absolute value, we don't have to worry about it. And then the sine of k pi is equal to 0. So the absolute value of plus or minus 1 times the absolute value of sine of n is going to be less than epsilon. And so this means that the sine of n less than epsilon. There will be an infinite number of n values such that and I guess technically the minus 0 actually does help. Uh, Woo! All right. I gotta type this up in LaTeX to also figure out how to use LaTeX. Uh, or I suppose these days Microsoft Word actually does fine. And then send it off to who's it? Michael Ecker, problem section editor. I've got another one too. It's a bit late, but nonetheless. So I've already got it in my head. I know how to solve it. It's not particularly difficult, but anybody who thinks they got it. with polynomial functions p of x and q of x form p of x times the sine of x, oops, nope, plus q of x times the cosine of x. Okay. Or, eh. Characterize with proof all such polynomials p and q. I mean, it's not the only proof you know. Yep, there is also one other thing that I did throw out there. If anybody can find it, does there exist a set of 3 squares that are linearly separated or can form an arithmetic sequence with each other, i.e. a squared, b squared, c squared, which can be rewritten as b squared minus x, b squared, and b squared plus x. Notice that every time that we move up 1 in the sequence, we're adding x, some number, which is going to make sure that these are also themselves squares. So that a squared could be rewritten b squared minus x, and c squared could be rewritten b squared plus x at the same time. And then with extension, find some b squared such that there are 4 or more such x values. Preferably an infinite number would be awesome, but you know, I don't know how far we can push this. I'm gonna hop over to PyCharm at some point during the next month, I hope, and attempt to just find some. My gut instinct is that there aren't, but I don't know, or more realistically, I don't know. I had a gut instinct at one point that I was like, absolutely, it could work. And then I was like, no, it can't. And I've been arguing back and forth. So I'll probably change my mind 10 more times before I can actually, like, show any of it. But I'll figure it out at some point. Alright, I think we're going to call it a night and raid out. But thank you, everybody, for showing. We are going to go find some friends. Who do we have? Ellie's still awake, goodness. Well, we got a few people. I think tonight we're probably gonna go see... You know what? Let's go see. Man. I'm always gonna have this, like. Decision paralysis. Let's go see Effin Funny. This is Sandeep Parikh, who was on The Guild. If anybody... He's playing Detroit Become Human, and I've heard very good things about it, so... Alrighty. We'll see you all later. I will be back on Friday. Yes. And we're going to see if we can get more FF7. I got to figure out if I can make OBS cooperate with FF7 any better than it currently is, which is to say it isn't. But we'll see how it goes. There is also the possibility that I have an update to OBS that I can't get because I'm in Linux and I'm just not downloading it properly, but at any rate, we'll see y'all later. This is Obi-Wan Pez for N Simplex Pachinko. Have a good night.